Hi everyone, this is Yulia Mikhailova, and I want to welcome you to our series of conversations with national labs at Princeton, organized by the Department of MAE. And today our speaker is Linda Young. And I'm really excited to introduce Linda. She is a distinguished fellow at Argonne National Lab and a professor of physics at the University of Chicago. Linda obtained her undergraduate degree at MIT in 1976, and she got her PhD in 1981 from the University of California, Berkeley. After a postdoctoral appointment at the University of Chicago, Linda started her research career in the physics division at Argonne National Lab, where she has worked on precision laser spectroscopy, electron scattering from polarized deuterium targets, atom trap trace analysis, and X-ray interactions with matter from the linear to nonlinear regimes. Linda is a leader in the field of atomic, optical, and molecular physics. She has served as the director of the X-ray science division of the Advanced Photon Source in Argonne. She has also been the chair of the Division of Atomic, Molecular, and Optical Physics of the American Physical Society. Currently, Linda serves on many scientific advisory boards and panels worldwide. She has been honored as a Fellow of the American Physical Society, Gila Visiting Fellow, and as a Helmholtz International Fellow. So I'm so happy to have Linda with us today, and we are ready to get going when you are. I'm turning things over to you.
Okay, well, thank you so much for the kind introduction and the invitation, Yulia. Let me share my screen now. And so Yulia told me you were kind of interested in hearing what's going on at National Labs, and I didn't want to go through a whole history of all the things I had done, but more focus on the current work that we're after. And so on this title slide, I figured, well, let me tell you about exploring ultra-intense X-ray interactions with matter. And this little right graphic over here actually shows a depiction of our very first experiment at the world's first hard X-ray free electron laser source that's located at another national lab, SLAC National Lab. And it shows how you can blow off all the electrons from a single neon atom in a single pulse. It's a very nice graphic anyway. And so I'm happy to be able to tell you a little bit about National Labs, and our national lab, my quote home national lab. So as Yulia told you, I've been there for a pretty long time, but not as long as it's actually been operational. So Argonne is the nation's first national lab. It was founded in 1946, and it was founded on the premise that they would find peaceful uses of nuclear energy. And it has evolved since that point in time to be a very large multidisciplinary DOE science-sponsored lab. And it has a couple of very large facilities associated with it. It is home to the ALCF, which stands for Argonne Leadership Computing Facility. There is a large-scale computer there now, and in 2021, they expect to have the nation's first exaflop computer there called Aurora. So that's like coming soon. And of course, we also have this APS that we've been talking about, which is the Western Hemisphere's brightest source of X-rays. And this is a picture of it. And when I was X-ray Science Division Director, I had to make sure that some, 60% of the beamlines on here were running properly for users and making other strategic investments so we can go to the next level. It actually got its first light some time ago, about 25 years ago, in 1995. And it's due also for an upgrade, just like the computing facility is due for an upgrade. And its upgrade will be in about 2023, and will increase the brightness of this X-ray source, between 50 and 100 times. So, it's lots of new toys keep coming up. These national labs have these big facilities, and they constantly expand their capabilities. And as soon as you finish building one, you worry about the next one, right? Yulia knows exactly. I mean, you have the Princeton plasma physics lab, right? I mean, I'm sure it's exactly the same thing, right? So since inception, Argonne has been run by the University of Chicago. The University of Chicago is a private university. It was founded in 1890. One very historic event, which led to the founding of Argonne, was Chicago Pile 1, the first man-made self-sustained nuclear reaction on December 2, 1942. It actually took place in a squash court in Stagg Field. Stagg Field has now been replaced by two libraries here. There's Mansueto Library and Regenstein Library. I'm told, and I think it's probably true, that this has the largest collection of books. So Mansueto Library, this bubble, actually has all of its books like underground. And it's retrieved when you go in, you ask for a book, and then some automatic retrieval system comes in and gets it for you. Anyway, but it's supposed to have the largest collection of books in the US, I'm told. The university administers both Argonne and Fermilab. And it claims 100 Nobel laureates, right? It really loves to claim everyone who walks through the halls at some point, I think, is a Nobel laureate, but they claim that. Anyway, so Argonne National Lab is a DOE lab, and DOE's labs have a mission, right? And it's an Office of Science lab. It's not one of the NNSA labs, the ones that have to do with defense. So the mission of the Office of Science is to deliver scientific discoveries and major scientific tools to transform our understanding of nature and advance the energy, economic, and national security of the United States. So I copied this right off their mission statement. I think it may change from time to time, but I copied this one very recently. And so we have this little AMO physics group. And because we have all of these very advanced X-ray sources, our little niche in this area is that we really like to come up with a predictive understanding of fundamental X-ray interactions with matter. And that is something that can underpin many other applications that you may use X-rays for. And while the APS is a source where the X-rays tend to interact with matter linearly because of its fluence per pulse, the new kid on the block, the LCLS, the X-ray for electron laser, stretches that out into the nonlinear regime, as Yulia well knows very well. Okay, so this is the new kid, the quote, new kid on the block, now 10 years old. And this is the LINAC coherent light source at SLAC. It's an X-ray for electron laser based on the last 1 kilometer of an existing 3 kilometer LINAC. It was proposed by Claudio Pellegrini in 1992 and came into realization in 2009 in April. So it uses the last third of 3 kilometer LINAC, which would normally go up to about 50 GeV. The reason that that this XFEL has come to SLAC was really the brilliance of Claudio to realize that, okay, well, in 1990, 50 GeV electrons are not actually so interesting for the high energy physics community. There was a Tevatron at Fermilab already. And so 50 GeV electrons are maybe not, the frontier anymore, despite the fact that it had already, been the progenitor of Nobel Prizes for the discovery of the J-psi particle and for looking at the quark structure of nucleons. And those were a couple of Nobel Prizes, back in the 80s and 90s. So he said, well, we have this great LUNAC. We can make a light source. And so what you do is you take your electrons, which they know very well how to control, and accelerate them up to 14 GeV or so, send them through an undulator, which is a periodic magnetic array, not just an undulator like you'd see at the APS where they might be 2 meters long, but actually a 100-meter long undulator. Think of this undulator that's, you know, as long as a football field. And then it would pass into a couple of experimental halls, the near experimental hall where we were doing our experiments and a far experimental hall as well. But what I want you to note is that, that this is actually a large collaboration. Although it's housed at SLAC, there were contributions from Argonne, Lawrence Livermore, and also UCLA, which was the home of Claudia. So Argonne actually fabricated all of the undulators that were used for this free electron laser. And Lawrence Livermore, I think, helped with the photon diagnostics associated with that. Okay, so what are these XFELs good for? Well, they really bring this large increase in peak brightness. There's a graph here shown that was made by Joe Storr, who was actually the first director of the LCLS. And it shows as a function of time the X-ray brightness that has gone up a lot recently. So these blue circles here have to do with the storage ring, the APS type X-ray sources. And the XFELs are these red things up on top. And this scale for brightness is the standard one, where it's photons per second per millimeter squared, per milliradian squared per 10th percent bandwidth. And so you can see there's this huge jump. And what that allows you to do is to look at nonlinear and multiphoton phenomena. And so what I'm going to tell you a little bit about is how we look at non-resonance response with intensities up to 10 to the 20 watts per square centimeter, which you can reach if you focus these X-ray beams. And also to look at resonant phenomena, where you can look for things such as Rabi cycling and stimulated Raman scattering and other such phenomena. There are other things that have been observed. Stimulated emission to form an atomic X-ray laser, some second harmonic generation, optical and X-ray wave mixing, but I'm not going to talk about those. Those are things that, you know, other people have been investigating. Okay, the other thing about XFELs is they're extremely versatile. And so you can have tunability from 10 eV out to 20,000 EV. I mean, it's just an incredible range that you can have. You have a huge pulse energy, and maybe it's like 10 to the 6 times more than for high harmonic generation. So on this graph, which is from a roadmap article that I made a couple years ago, you can see the XFELs up here in the orange, and the high harmonic sources down here sort of in the purple. And they each have their own advantages. The XFELs have huge pulse energies, but slightly longer pulse durations. And the high harmonic source can get you down easily into this sub-femtosecond. So here's 1 femtosecond across here domain. But they don't necessarily go out to super high photon energies and correspondingly small wavelengths that you might want to have to probe atomic structures. The XFELs are all, but the other, besides having very short pulse durations, the other huge advantage that these HHD sources have is that they're completely synchronized to the pump pulse. And so that's a huge advantage as well. But the XFELs can give you multi-color, multi-pulse, sub-femtosecond pulses with, you know, variable time delay. So they're just extremely powerful. And this little graph that I made is actually already outdated because XFELs have extended their reach to sub-femtosecond in the last year or two. Okay. So how does this XFEL work? So you have your electron bunch, and it traverses this undulator, this periodic magnetic array. As it starts, the electrons are uncorrelated, but as it passes through the undulator, every time it goes through one of these periods, the electrons emit radiation. The radiation interacts with the electron bunch. And as you go down the undulator, you eventually form these microbunches. And these microbunches then radiate coherently. And the radiation wavelength that you get compresses the undulator wavelength, which is on the order of 3 centimeters, by this relativistic factor gamma squared. And it can, so you can take things that are centimeters and turn them into Ångstrom. And it's tunable both by the gamma, by the energy of the electron going in, and also by this K factor of the undulator, which is basically the strength of the magnetic field. And the power gain length, so you exponentially build up power as you traverse this undulator, and the power gain length is basically given by the undulator wavelength, but divided by this very important FEL parameter rho, which tells you how long, which is a measure of how intense is that electron beam as you come in. It's typically on the order of part in 10 to the 3-ish. But when you build up this radiation, right, it starts with sort of amplified. It starts with spontaneous emission, which is chaotic in nature. And so you can do a simulation for actually what comes out at the other end. And this is a simulation for the European XFEL for a single pulse at 1 Ångstrom wavelength. And you see the temporal properties here on the left and the spectral properties. And what you can see is that everything is very spiky. And you get hundreds of spikes in an electron bunch. And the spike duration is given by this cooperation length, which is the radiation length times the gain length over the wavelength of the undulator. And you can get a spectral bandwidth, which is on the order of this FEL parameter that I referred to previously. So all these things are, properties of the FEL, but you notice that the duration is on the order of 10-ish femtoseconds or so, and it's very spiky. But this is okay, although it's not what you might like to have for your laser, right? It actually works rather well for a number of applications. And this is the application that was actually the poster child application for the LCLS. So the LCLS and other free electron lasers cost on the order of $1 billion. So you have to have a good reason to want to build them, right? Besides just making good use of, an accelerator that has maybe become not so interesting for the high energy physicists. And the poster child experiment that really sold this to the DOE was something called single molecule imaging. And here the idea is you take this complex protein molecule, you drop it into this bright LCLS beam that has about 1 trillion photons in, say, 10 femtoseconds or so. And then you measure the scattered radiation, both in wide angle and in small angle. And by taking all these diffraction patterns, you should be able then to reconstruct the 3D structure of your complex molecule. And so this was, clearly a huge boon for the biology community, because typically when you want to find out the structure of a protein, you have to crystallize it first. So you crystallize it, and then you take it to the synchrotron, and you measure all, the diffraction spots, and but many of the systems that they're interested in do not crystallize well enough to be able to get a good diffraction pattern at a synchrotron. So this would be a huge boon if you didn't have to crystallize. But there are AMO questions when it comes to what's going on in that system. So we'd like to understand the fundamental nature of X-ray damage at high intensity. This is the seminal paper in the year 2000 by János Hojdú and his collaborators that was published in Nature. This was right when the LCLS was given the green light to go. And this is a picture of a lysosine molecule before the X-ray pulse hits it. And then during 10 femtoseconds, it's still more or less intact, but after 50 femtoseconds, it's really blowing apart. And so you capture the diffraction pattern in the when the pulse is on. And this simulation had 3 times 10 to the 12 X-rays and 100 nanometer spot at 12 keV, giving this extremely high intensity, 10 to the 22 watts per square centimeter. But it's a simulation, so you can simulate whatever you need. So that put a target. But even before all this Coulomb explosion happens, there's electronic damage that's going on. The electrons are moving around. We'd like to know what's going on there. That's kind of an AMO type question. And of course, it's interesting to just understand what's the behavior at 10 to the 22 watts per square centimeter. Of course, interesting to understand nonlinear X-ray processes, the role of coherence. Maybe you can even do quantum control of inner shell processes in the same fashion that you do things, in the visible with outer shell electrons. So all these things are topics for investigation. I'm just going to quickly run through, some of these first experiments. We wanted to look at the nature of electronic responses. It was actually the first experiment at LCLS. And then we had effluence at 10 to the 5 X-rays per square Ångstrom. We were able to vary the pulse duration between 80 and 340 femtoseconds, and actually the photon energy by varying the electron energy going through the undulator from 800 to 2000 eV, and thus achieve around 10 to the 18 watts per square centimeter. This, of course, far from the original imaging parameter. And we chose that we would just, we'll start with a well-characterized target. We know very well about neutral neon with the 2s and 2p shells, and also the 1s, they're energetics. We know that if you do inner shell excitation, you can get an Auger yield of about 98% with a very fast Auger clock. And because we have the tunability and energy, you could actually change how you interacted with the neon atom from talking both to the valence shell when you're below the threshold for the 1s electrons to talking to the inner shell above 870 eV. So this is looking at the outer shell, and this is the inner shell. Okay, what we found was that unlike all things that happen at synchrotrons, we would get sequential multiphoton processes. There were never any multiphoton processes at synchrotrons. And in fact, in one single pulse, you could strip all of the electrons from neon in with the sequential mechanism of photoionization, Auger, and so on and so forth. But when you tune below that 1s threshold, you would actually just strip off all the valence electrons. So it's a way that you can control what sort of product you make just by controlling the photon energy. You can make helium-like neon, or you can make bare neon, and you can also do things in between. And so we figured all that out and could model it with theory fairly well. Those were all non-resonant processes. But we could actually look for resonances and see, oh, maybe we can control inner shell electron dynamics. And so that absorption spectrum of neon that I showed you before was actually a bit too crude. If you go near the 1s threshold at 870 eV, you actually see that there's a Rydberg series in neon going up to that 1s threshold. And you can try to sit on this 1s to 3p resonance, and you can try to do Rabi flopping here. You can calculate that the intensities needed to do that are actually in principle there. And then you can see, well, what, would we actually be able to do this? And one idea is that, oh, if you can do this Rabi flopping, you can inhibit the Auger decay, and therefore you can inhibit the X-ray damage. So here is what would happen if you did this 1s to 3p excitation. What would happen after that? Well, one thing is that 3p, you could try to eject that into continuum. That's highly unlikely. You could eject one of these other inner valence electrons out. That's also unlikely. But as you can see how huge this resonance is, the most likely thing actually is to do this Rabi flopping if you're tuned precisely on resonance. So we figured, oh, well, let's take a look at this. And what we would do is we would scan the X-ray energy and we would look for Rabi flopping. The signature would be a broadening of this resonant Auger peak. And we were doing this with a single pulse, where the first pulse produced, we decided we would do this not on the neutral, but rather on the ion. So we took the first part of the pulse to eject a 2p photoelectron. And then we would operate on the 1s to 2p rather than the 1s to 3p, because the 1s to 2p is much stronger. And we'd look for broadening on that particular transition. The broadening is a little bit hard to see here. On the next slide, I'll show you how you can see it if you look very precisely. But maybe a more important thing is actually that this high fluence pulse really alters the target. Now suddenly there are all these other hidden resonances that are in the system because you're making all those ions. All those ions have resonances, right? And these resonances are much larger than the background. So here's a picture of some of those resonances associated with that. Here's the Rabi flopping signature. You can take a look at that Auger line width when you're exciting non-resonantly versus when you're exciting resonantly. These are the blue dashed the blue markers here. And if you extract out what it should be, you can see that the resonance signal is, has this broader wings than the non-resonant. So there's a little bit of broadening. If you do some theory associated with this, you see that much of this is due to the fact that we have a Sassy pulse rather than a really nice Gaussian pulse. If you actually had a Gaussian pulse that was doing the excitation right on resonance, then you would see these sort of nice wings if you had that same intensity rather than just this long, broad tail. Okay, so anyway, we know that there are resonances. We know that we can, try to do some inner shell excitations with it. Looks like I'm behind, okay. But then we say, oh, well, can we account for resonances and relativity in these complex systems? We're going back, oh, we understand atoms. Now let's see if we can understand something more complex. In the atoms, it turns out that we can actually track what's going on. This is a model for the argon atom where the single photon absorption up to the point where the next photon cannot ionize because it's below the binding energy for that next ionization state, was good to model some things, but there were cases where you would see that resonance can induce damage behind that sequential photon absorption model. And that was that we published in 2014 for the argon atom, where you can see the final little resonance states were out here in the end that actually got you to this unexpected high charge state. Similar effects would happen in heavy atoms. This is in xenon at 5.5 keV. You could look at both relativistic effects and resonance effects. The resonance effects are a little bit more important than the relativistic ones. So now we say, okay, we know atoms. Can we do something with these complex species? So Fei Ho in our group made an atomistic model for high intensity X-ray scattering. And here you have the X-rays propagating with linear polarization, interacting with a nanoparticle, and you actually simulate what you would expect in the diffraction pattern. It is basically a product of the form factor for this nanoparticle that you have. That's a function of both Q, the scattering angle, and time, because it's evolving as you go through all these different states. So you can calculate what that is on an atom by atom basis and sum it up to get the form factor of the nanoparticle. Then that gets involved, of course, with the current from the X-ray pulse itself and then the Thomson cross-section. So you can calculate all these things, and simultaneously, this is actually using the supercomputer at Argonne, where you follow 50 million particles simultaneously. You can simulate what you would expect for a 30 femtosecond pulse with the standard imaging fluence at 8 keV. And you can see that in a 30 femtosecond pulse, that things are really falling apart very rapidly. But if you have a 2 femtosecond pulse, then things are still sort of intact. And so you can actually reconstruct the structure of this particular system. And we actually showed that in this article in 2016. Of course, there are also issues having to do with resonances. And this is not just a simulation, but actually a comparison with experiment that was published in this year. And here, what was done was we had a bunch of sugar balls that were illuminated at these different photon energies, ranging from about 1.5 keV down to about 530 eV. And what was interesting about it was that we thought the photon flux associated with the incident radiation would be this yellow line here. But in fact, if you would calculate what you expected that incident flux to be from the scattering that you detected, you would see this line down here if you're assuming a linear scattering model. And it turned out that, so this was, a sugar ball has carbon, nitrogen, and oxygen in it, and it's inside a water droplet. So you try to go into the water window, which is below 540 eV. So then you irradiate it at 530, and that's where you got this huge drop, order of magnitude smaller scattering than you expected. And so why is that? So it turns out that at that photon energy where it was being irradiated, this is actually in collaboration with Janos Hoydu, the person who is the originator of the single molecule imaging, diffract before destroyed concept. And so as biologists, they say, oh, let's just go into the water window a little bit and let's just go there, right? But of course, as we know, there are these resonances when you kind of get near the edge. And so if you happen to hit these resonances, you can see that the form factor associated with those resonances are evolving during the pulse. And this is what it's showing, originally it was just below the oxygen K edge. And so you would see this situation, then you would ionize, and then you'd have a new absorption spectrum, and then that would Auger decay, and then you'd have a different absorption spectrum. So it's very, it's complex. So we were able to understand the observations with phase modeling, and these transient electronic structures really alter the scattering strength, and it tells you what sort of optimal pulse configurations you would like to have for these sorts of imaging experiments. So what we want shorter, more intense pulses, right? This is a typical thing, right? This is always what people want. Why? Because of imaging, looking to follow intershell dynamic processes, also being able to have attosecond probes at different atomic sites. There are many different things that you can do, right? So our friends at SLAC have been very busy working on this. So the temporal structure of SASE-FELs, there's a single spike pulse duration limit that depends on the electron bunch duration and the radiation wavelength. It's given by this cooperation length that I mentioned before, which is the slippage within one gain length, which is given by these parameters. And so what you note on this is the spike duration is proportional to the wavelength of the radiation. So you can get shorter pulses in the hard X-ray range easier than in the soft X-ray range. And so there were some demonstrations of this earlier on, where you could get single spike durations of less than 1 femtosecond at an angstrom. But when you go to 10 angstroms, this is very tricky. So these were a couple of demonstrations, experiments at LCLS. This was at 5.6 keV, which is maybe closer to 2 angstroms, and 5.6 and 9 keV. And in both of these, it's some hundreds of femtosecond pulses were estimated by measuring the spectrum. And these kind of limited pulse energies. Typically, you get pulse energies that are several millijoules out of these FELs. So think of it, millijoules in 10 femtoseconds or so. But to go to soft X-rays, the idea was that you would have to really tailor that electron beam more. And this was an original concept of Sasha Zolens, who's actually at Argonne. And the idea is that you could superimpose a laser onto the electron beam when going through a wiggler. That would cause an energy modulation of the electron beam, which then when going through a magnetic chicane would turn into a density modulation, which would then be this ultra short spike that could be amplified through the rest of the undulator. It turned out, amazingly, that after buying the laser and putting it all together and having it fail, it was found that you didn't need the laser at all. It was amazing. Turns out that the electron bunch current isn't really a flat top. It actually has this tail. And usually the accelerator physicists like to chop off the tail so that you have a nice electron bunch going through the undulator. But if you don't chop off the tail, that tail radiates when it goes through the undulator. And so that can be used to modulate the electron beam before it goes through the chicane. And so so that whole scheme can work even without a laser, which is amazing because then it's actually scalable to high repetition rate, whereas a laser would be pretty tricky to do that. So there are these exciting developments in X-ray lasers. This actually is a paper that just came out in Nature Photonics that demonstrate a single spike at almost a keV. And you can also imagine having 2 colors, sub-femtoseconds, and also at high repetition rates. And so these are all things that are just coming, for the future. It's really quite amazing. And this is just something that we decided we would actually investigate, and that's looking at attosecond transient absorption with XFELs. And the reason is all these nonlinear things that we've been looking at have typically been done on single particles. But then you can ask the question, what actually happens when you actually propagate resonantly through matter? And so with Meta Gard and Marie Lebay, we have this TDSE and Maxwell wave equation approach. And what you see is there's a big energy exchange between the medium and the field, and you can see all these different phenomena. This theory also reproduces earlier experiments that demonstrated X-ray lasing and stimulated Raman scattering at LCLS. We have a nice experiment to prove that European XFEL, so we're excited to do that whenever we're able to go, right? It might be remote, but let me just summarize. AMO physics experiments in theory have established a basic understanding of the response of matter to ultra-intense XFEL radiation. There are a number of things that have been investigated, and the understanding will aid in this quest for single molecule imaging and other applications like chemical imaging. I think the future is very exciting with attosecond pulses, multiple color configurations, high rep rates, all these good things are happening now. These XFELs are not just in the US, they're actually all around the world. So we travel to different places to do our experiments. I mentioned that we have this resonant propagation experiment at European XFEL, that's in Hamburg. So that's fun. And the LCLS2 is coming online now, but its high rep rate won't come on for another year or so. But it now has tunable undulators, so you can tune the radiation not by tuning the electron beam energy, which to people who are used to synchrotrons think that's really interesting, funny. I wanted to show the AMO group in September of 2018, the last time we actually gathered to make a picture. This is our group. We have 5 staff members and then a number of postdocs and students. These are the people who've replaced the people who've left, and others have gone on to various places. Our last 2 postdocs, one went to a university in Tokyo, and one went to Paul Scherrer Institute in Switzerland. And these are our 3 new postdocs and a new student here. And so we meet every morning. This is a picture from one of the mornings I thought I would take. So you can see that, So one of our postdocs is in England. Anyway, So I thought I'd just end here, and you probably have lots of questions. I'm sorry I went a little over time, but okay, I'll stop sharing my screen and we can chat. This is really a team effort, and it's not just our team. It's teams from all these different facilities that make these things happen, which makes it kind of fun.
Thank you so much. Thank you for this wonderful talk. I really, really enjoyed it, and I'm sure everyone. So we have a lot of questions. First question is there a limit to how short you can make the electron bunches?
Is there a limit to how short you can make the electron bunches formed by the undulator? Well, the electron bunches aren't really formed by the undulator. They're formed prior to going into the undulator. There are bunch compressors that actually compress their duration. So typically, when you want to make shorter X-ray pulses, what you can do is you use those chicanes. So you disperse in space the electron distribution by their energies, and then you can put a slotted spoiler there and just chop out a little bit of the electron bunch, and then it becomes very short that way. And there are other mechanisms to do that too. That way, of course, just slices out a little part of the beam, as opposed to actually doing a compression, which gives you more electrons per unit time.
Thank you. So another question is, what peak power of X-rays and photon energy are needed to realize diffraction before distraction of single protein imaging?
Well, this is a very good question, right? So actually, the most successful thing at the LCLS has been something called serial femtosecond crystallography, where instead of having uncrystallized particles to image, you actually have small crystals that you image. And there already, there's, even with what we have now, at rather modest intensities, you're able to get very good reconstructions. And so then you can look at crystals that are maybe a micron or less, as opposed to the crystals that you need at a synchrotron, which might be 10 microns or so. For imaging with the without crystallization, the so-called single molecule imaging, then you really need this. It depends on your particular system. So what we were seeing is this 10 to the 20. Watts per square centimeter. This is what was working for I guess the Argonne cluster that we looked at, but many other people have been looking at this in other ways, but it's a little bit higher. And the point is actually that getting atomic resolution on those things is quite hard. And so people are actually going down to the slightly longer wavelengths to do those imaging, and are becoming more satisfied with nanometer type resolution.
Okay, thank you so much. Just maybe last technical question, research question, before we switch to career type questions. What is the repetition rate of current X-ray free electron lasers, and what is the repetition rate of a new LCLS 2 arm you mentioned in your talk?
Okay. So most free electron lasers run at about 100 hertz or 120 hertz. That's how we did all those initial experiments. The new LCLS 2 can run up to a megahertz. It will be the first superconducting first X-ray for electron laser based upon superconducting accelerator technology that is running CW. The European XFEL actually also is running a superconducting accelerator. has superconducting modules in its accelerator, but it does not run in CW mode. So it runs in bursts. And when it runs in bursts, the bursts come at 4.5 megahertz. And then each burst comes at 10 hertz. And so they run up to about 20 kilohertz in this fashion. So it's different, right? But when the LCLS2 actually comes up, it can in principle run at a megahertz, but I think most people, just because when you run at a megahertz, there are a lot of issues with detectors and other things, which I didn't talk about at all. But so maybe people would like to throttle it back to more like 100 kilohertz or so.
Okay, thank you. Thank you so much. So next question is, can you describe some of your experience working with LCLS? How much laser time do you get? How much setup for the experiment do you do?
Yeah, sure. So at LCLS, you only get time based upon a competitive proposal process. And so there's maybe a 1 in 5 chance that you'll get beam time if you submit a proposal. And then you get typically 5 shifts of 12 hours each. So you prepare for a very, very long time before your LCLS or European XFEL or whatever beam time, because you almost never be granted a repeat experiment. So you have to get all the data you need to make a publication or to make a story in that one beam time. So I would say there's a huge amount of preparation, even though you only get 60 hours of beam time. But it's actually extremely fun. So how do you do this? You actually, you work a lot with the beamline scientists who are there. I didn't actually show a picture. I should have showed a picture of, so there's kind of 3 groups that you work very closely with if you're in AMO, because you work with your group who's interested in the science. You work with the beamline, the instrument scientists, who know all about the intricacies of the actual end station. And you work with the accelerator physicists, because in AMO, you're always wanting to change the characteristics of your pulse. And so it's actually an extremely educational situation. In addition, you work with the detector physicists, because the detectors are, you can imagine when they're going at high rep rate and multi-pixel to capture some of these images, that it's really a lot of data, right? Because let's say you get snapshots at whatever, 16 megabytes per shot, and then you're going at even 100 hertz, gives you a lot of data. And then you don't have just one camera, but you have other cameras that are doing the diagnostics of your electron bunch. So you get an education in accelerators, detectors, instruments, and also big data, because it turns out that you record all your data shot by shot, and then you replay the data on their computers later to sift out what you would like to learn. So you know, I would have to say it's very educational. It's very interesting.
Thank you. There is one more question about research. I have to ask it. What is the most challenge you face to shorten the XFEL pulses? And also, what about issues with secondary radiation generated by accelerated electrons?
What is the greatest challenge? Well, it really depends on what you want out of the XFEL pulses. If you only want a short pulse and you don't need high intensity, it's not so difficult. You can just, you know, put in the emittance spoiler, and you can do these compression techniques. So you can put the, you can artificially, shorten your pulse that way. I think the hardest part is to actually make it both intense and short. And that's where all of these interactions with the enhanced SASE pulses are important. Yeah.
Thank you. So another question is, how does being part of a national lab affect your experience as a university professor compared with those at the University of Chicago Physics who are not part of Argonne or Fermilab?
Well, that's kind of an interesting question. Yeah, well, so
I wish I have asked this question myself.
I would say, so the one thing is that usually I would not be at the university. So the interaction with the student body would be less than if I were at the university. Argonne is about 25 miles away, but nowadays there's like no interaction anyway. So it's a little bit funny. And so the course I taught online this spring was all virtual, and I would say that worked fine. It was probably the same as any other professor, but you miss out the maybe the day-to-day interactions with the students and other professors.
Thank you. And then there is a related question. How has the current pandemic affected collaboration efforts and communication for you?
Well, let's see. I would say that it hasn't affected it as badly as maybe some other researchers, partially because we have these daily group check-in meetings every day at 10 o'clock. We have a check-in meeting and we all meet and we discuss, and we have journal clubs. But we also, because we do a lot of our work remotely at these expos, we also have gotten used to having collaboration meetings with them. So I also have like weekly collaboration meetings with the people at European Expo, and we all join on and we share our stories about the pandemic. We're so jealous of them. They're all back at work. So yeah, no, so it's actually quite interesting because we have collaborators in, for our European Expo experiment, we have collaborators in Hamburg, Heidelberg, Uppsala, Singapore, in lots of different places. And so, it's interesting. And we hear the news around the world this way. So.
That's great. Thank you. Do you know the landscape for the number of careers in the lab within the next year due to COVID?
Well, what's interesting is that as far as I know, our funding is not actually, it's not like being in a business. It's the government that's funding you. And it actually hasn't gone down. Right? So I would say it's rather stable as far as I know. And actually, I just got another grant with some people who want to understand initial processes in radiolysis having to do with nuclear waste tanks. So I would say that you never quite know about these catastrophes that happen nationwide, but sometimes the government likes to stimulate things, right? And so then they put out extra calls for research in different areas. There are, of course, calls in quantum information. I'd have to say that's one of the big things, right? That's not what we do, but that's one of the big things. And there is a big quantum information center at the University of Chicago, Argonne, and a number of places. It's called Chicago Quantum Exchange. If you look it up on the web, you can see it. They have postdoctoral and other sorts of openings there. So I would say it's not so different. On the other hand, the things that I do are extremely or that our group does, they're extremely basic. There are not so many people who do the things that we do. Many people investigate, Argonne is really well known now for energy storage, electrochemical energy storage, and lithium-ion batteries. There's a huge, area in that. There's also quite a bit of emphasis now on tech transfer to industries. So, there are things like that that are popping up that I'm just not so familiar with. But it's definitely, one of the things I think that the lab is pushing.
Another question is, does classified work get in the way of your collaborations with universities? In your collaborations as an Argonne National Lab researcher, collaboration with universities and also internationally?
Well, we don't do any classified work, so it doesn't get in the way of our particular type of research. There is classified research that goes on. And a long, long time ago, I had a colleague who was doing precision atomic structure of uranium. And he got his lab notebooks like confiscated. So well, because, maybe these transition energies were just extremely important and they had to be whatever, sequestered or something. So I don't have any experience with classified research, and there is very little that actually goes on at Argonne. It's not at all like Livermore, where some large fraction of the lab is behind the gate.
What is your favorite part of working in Argonne?
What's my favorite part? I would say my favorite part is working with my colleagues and all the other experts that are around the lab. They're very helpful in many ways. Yeah, so you can learn a lot from just all the different people who are out at, that are around at Argonne. So I would say there's a tremendous resource in that way. I would say that's, it always is, don't you think? Anywhere where you go, it's always your colleagues that make it nice, right? I would have to say.
Right, I completely agree. Thank you so much. So the next question is, what is the situation with gender and racial diversity in Argonne?
This is a very interesting question. This is a big thing now, I think, both at Argonne and Chicago. With gender diversity, actually Argonne is pretty concerned about this. And they have on their website, you can actually look at it, the gender and racial makeup of all the different types of employees at Argonne, ranging from senior management down to undergraduate students. And so you can actually look to see what they have. There are now a fair number of sort of senior managers, division director level and up who are female. I think there are 0 who are Black, though. And they have it divided into many different, components. And what you'll see actually is that there's a huge, there's a large number of Asians in sort of the postdoctoral and the research staff. And maybe that's to be expected, but that's kind of how it's made up. So if you're really interested in those statistics, you can go poke on the website. And I think they try, right?
What about your group?
My group? Well, there's myself, and then there's one other female staff member who, like you, has childcare issues. And there are 5 staff members. And I'm afraid all the postdocs are male and the student is male. But sometimes we get students and undergrads who come through who are female. I think I showed you a picture of our group at some point.
Right.
Yeah, so, you know.
What is a typical...
Any of you guys who want to come, or girls, right, who want to come and work with us, I'd be happy.
Thank you. What is a typical career path? Do you start for a graduate student or postgraduate? Do you start as a postdoctoral researcher and then you could be transitioned to staff member?
At Argonne?
Yes.
I would say that is a path, but one should not come to Argonne with a postdoc expecting to get a staff position. Staff positions are very hard to actually come by because typically they're funded by programmatic funds. And so what does that mean? So for example, for my group, I have to go out and find, you know, several $1 million to support the group. And to find another like, whatever, $350,000 to support another staff member, that's pretty hard. Whereas finding maybe 150 to support a postdoc, because if you have a staff member, then they have to stay for a long, you expect them to stay for a long time. And a postdoc, you know, 3 years or so. So it's a little bit, and the program funds get reviewed once every 3 years. So it's I would say it's hard to get a staff position, but it can be done through the postdoctoral route. But I would say it shouldn't be expected. That's for sure. There is actually a very nice postdoctoral fellowship called the Maria Goeppert-Mayer Fellowship. So Maria Goeppert-Mayer, you know, was the second woman to win a Nobel Prize, and she was at Chicago. And she did her nuclear prize, her Nobel Prize winning work at Argonne. She worked in the physics division where I first, you know, started. We have a nice plaque for her. It was designated an APS historic site. And guess what? She did her doctoral thesis on 2-photon absorption, which is what we study. It's amazing. So anyway, but there's a postdoctoral fellowship that's given out in her honor. And so if you win one of those, then you have maybe a better chance because it's hard to win one of those.
Is this fellowship for everyone, or is it targeting female researchers?
No, it's for everyone.
And anyone can apply.
Yeah, well, you have to have an Argonne sponsor, right? To apply, you know, because it's not just to do independent research. It has to be research, you know, somehow in the interests of Argonne. And then they like to give that to people that they think are so great that they want to keep them on as staff. It comes, I think the application is due every October, near October. So if there are any of you who are out there who are interested, you know, and want to work in the area that I work in, you know, you should, you know, contact me. But, you know, we're such a small part of the lab compared to all the other things that go on. There are many other, you know, avenues of research.
Thank you. So what advice can you give to someone who wants to join Argonne National Lab? A graduate student, for example.
Oh, a graduate student?
Yes.
Who wants to be a postdoc or wants to do graduate work at Argonne?
Let's say he wants or she wants to join the National Lab. What would be the first step?
Well, one thing, which is actually quite interesting, if you are a graduate student, and let's say you want to do some of your research at a national lab, some part of your thesis research, there are grants that are given out by DOE, SGS some type of student research grants. I think those are also in the fall, or maybe in August or something. And so then, let's say there's a grad student who wants to do something related to something at the National Lab. Then they can come and they get paid for all of their expenses. And then they do something having to do with their thesis at the National Lab. Then they can actually see what's going on at a National Lab rather than jumping in cold turkey as a postdoc. But of course, you can also come in just as a postdoc. But I think this other way, they really, I would say it really helps because then you get to know the people at the National Lab who, you know, maybe have similar interests in where you would like to go. We have, one of our postdocs was actually a student of somebody who would come to the APS to do research, and then was doing, you know, pump probe molecular dynamics with X-rays and lasers. And so he became a postdoc in our group, but he was sort of introduced to our group by coming there for some experience. So I would say that those two ways are good. You have to make some connection to somebody at the National Lab.
So if you just respond to some call for open positions, it will...
that will work too. So let's see, that was one of our postdocs. Another postdoc who is from Greece, France, Sweden, was a student of a collaborator of mine, right? So then you get to know them that way. But the third postdoc, the one from England, actually just responded to a call, and he gave a a Zoom interview, and we liked him a lot, and we hired him, and he's been fabulous. So, you know, anyway it works, I would say it's maybe a little bit easier if you know somebody. Or if there's some area of research that you want to target, do a little research, do some outreach, and then respond.
Thank you. So, and perhaps the last question for today is, what are some of the biggest challenges you faced in your career path?
Well, I would say it was challenging when I was named group leader, when I was the youngest person in the group, and everyone had been there longer than me. That was a challenge, right? I was not sure I wanted to do that. But the division director said, no, come on, Linda, you can do it. And then we had to sort of change directions, right? We were doing something, and then the advanced photon source was coming up. And so then we had to change into this sort of X-ray direction. I mean, this is a pretty long time ago now, right? But before we were doing other things, right? And so that, I would say that was a bit of a challenge. The other challenge is just infinite paperwork. So much bureaucracy is always a challenge.
How did you manage it, the first challenge of being a young leader?
Oh, well, I consulted and found good people to hire. Because there were some people who were going to retire fairly soon. And so, you know, you have to build up a good team. And so I would say that was helpful. And then also, you know, it was helpful to have the division director, you know, there for advice to talk to. He was a male, and he was a white male, right? So he was one of the privileged classes. But, you know, it's just good to have a good relationship with people. And, yeah.
Thank you so much. Thank you again for this fantastic talk and for all these answers. I think it's extremely useful for us to know all this path.
Okay.
And, right. So,
well, I hope you all enjoy your graduate career at Princeton. It's certainly a you know, premier institution, and I wish you all good futures.
Thank you. We have some applause via Zoom.
Okay, very good.
Thank you. Have a great day, and everyone, and Linda, and bye-bye.
Bye-bye. Thank you, Yulia.